Hello and welcome to my lecture series for Control System 1, which is designed for 5th semester BTech Electrical Engineering students. Myself, Shuman Ghosh, as a course coordinator, assistant professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This particular PPT is designed for lecture 13, 14 and 15. And today is our 14th session, and these are the contents of 13, 14 and 15. And in our 13th lecture we already discussed what is characteristics equation and why it is called characteristics equation, pole locus of a standard second order system with variable damping ratio, and stability by pole allocation. These first three topics I already discussed in lecture number 13. In today's lecture, that is lecture number 14, we will discuss on Routh-Hurwitz criteria and its application and some workout problems. And more workout problems will be there in lecture number 15, and in lecture number 15 there will be another topic, that is relative stability. So for today's lecture, just go to the Routh-Hurwitz criteria and some workout problems. And before going to Routh-Hurwitz criteria, let us take one quick recap of our previous lecture number 13. So this is our characteristics equation, 1 plus GSHS is equal to 0. That is called characteristics equation. And stability by pole allocation, here we concluded in our previous lecture that if the poles are present in this green zone, that is negative real axis part, then the system will be stable, and if the poles are present at this red zone, that is positive real axis part, then the system will be unstable. So moving to our today's topic, that is Routh-Hurwitz criteria or Routh-Hurwitz stability criteria. Now, the characteristics equation of a simple feedback control system can be written as Fs, that is transfer function, or Fs is equal to the characteristics equation is equal to 1 plus Gs into Hs. Or in general, we can write An s to the power n plus A of n minus 1 s to the power n minus 1, A of n minus 2 s to the power n minus 2, like this way, and it will end at A0 is equal to 0. This equation is termed as characteristics equation, where the order of the system is n, that is nth order characteristics equation in general. Now there are two necessary but sufficient conditions for the roots of the characteristics equation to be lie in the left half of S plane, and we already know that left half of S plane is called stable region. So two necessary and sufficient conditions are all the coefficients of this particular equation, that is An, A of n minus 1, A of n minus 2, like this A0, have same sign. It should have. None of the coefficient vanishes. Now, how we can form the Routh-Hurwitz table? Now suppose this is our characteristics equation. Now from this particular characteristics equation, if we want to calculate the stability of the system, then we have to form the Routh-Hurwitz table first, or Routh-Hurwitz chart. So if we want to calculate, just take the higher value of s. Here the higher value of s is s to the power 6. So here higher value of s is s to the power 6. Okay, so just put s to the power 6 here, then just take the coefficient of s to the power 6, that is a6. a6 is our coefficient of s to the power 6. Then just put the coefficient of the even power of s to the power 1, s to the power. So put the value of put the coefficient of s to the power 6, then put the coefficient of s to the power 4, then put the coefficient of s to the power 2, and put the coefficient of s to the power 0, like this alternatively. If we started with s to the power 6, then you have to put the coefficient of s to the power 4, then coefficient of s to the power 2, then coefficient of s to the power 0, like this way. Alternatively put the coefficients starting from s to the power 6. Next, s to the power 5. Next, the lower value of s to the power 6, that is s to the power 5, and put the coefficients in alternative way, that is a5, a3, a1, like this. Now if we want to calculate the coefficient of s to the power 4, or the value of this particular position, if we want to calculate, then you have to multiply like this into this minus this into this. That means a5 into a4 minus a6 into a3 divided by a5. So that particular result you have to put in this position. Okay, now if we want to calculate, or if we want to find the value of this particular position, then we have to use the formula like these into this, that is a5 into a2, a5 into a2, then minus a1 into a6 divided by a5. So put the value here, and for this equation you have to put a5 into a0 minus 0 into a6 divided by a5. So that will result a0. So here a0 will be there. So for this position you have to put a5 into a4 minus a3 into a6 divided by a5. For this position we have to calculate a5 into a2 into a1 into a6 divided by a5. And for this position you have to calculate a5 into a0 minus a0 into a6 divided by a5. So put the value here. So that is our A, capital A, that is our capital B, and that is a0. And now if we value S3, if we want to calculate the row of S3, then just multiply this into this and this into this. So A into A3 minus B into A5 divided by A, that will put here. So that will again represent at C as C, like this way. Like this way you have to calculate, or you have to find all the positions value of this Routh-Hurwitz criteria we have to calculate. Now how we can find the stability of the system? Now to find the stability of the system or the stability of the system, just look at the first row. Look at the first row. If in the first row, in the first column, just look at the first column. If in the first column there is any sign change, that means positive to negative or negative to positive, if all the variables, if all the values are of same sign, then the system is stable. If there is any type of sign changes, that is positive to negative or negative to positive, then the system will be unstable. So here is a conclusion: the roots of the equation are all in the left half of S plane. That means the system will be unstable if all the elements of the first column, that means in that column, all the elements of the first column of the Routh tabulation are of same sign. The number of, now here we can say that the system is stable or unstable. If there is sign change, we can say the system is unstable. Now if the system is unstable, that means there are some poles in the right half of S plane. Okay, now if we want to calculate how many poles are there in the right half of S plane, so that the system is unstable. So if we want to calculate the number of poles that are present in the positive real axis or in the right half of S plane, then we have to see the number of sign changes. If there are 2 sign changes, then there are 2 number of poles present in the right half of S plane. Now just take one example for better understand. Let us take one example. This is one transfer function and we have to calculate whether the system is stable or not. First, write down the characteristics equation. So the denominator part, put the denominator part is equal to 0. That will be our characteristics equation. So s to the power 5 plus s to the power 4 plus 3s cube plus 9s square plus 16s plus 10 is equal to 0. That is our characteristics equation. Now apply the Routh-Hurwitz tabulation. Here the highest power of s is s to the power 5. So just put the value of s to the power 5 and put the coefficient of s to the power 5 here. Now for this equation, the coefficient of s to the power 5 is 1. So here 1 will be there. Now alternatively put the coefficient of s's. If you start by taking the coefficient of s to the power 5, then we have to take alternatively, that means you have to take coefficient of s to the power 3, then coefficient of s to the power 1. So you have to take the coefficient of s to the power 3, that is 3. Then you have to take the coefficient of s to the power 1 alternatively. So it will be 16. So 1, 3, 16. Okay. Next, take s to the power 4. Now the coefficient of s to the power 4 here is 1. So 1 will be there, and alternatively s to the s square, that coefficient of s square is 9 and coefficient of s to the power 0 is 10. That's why we write these first two row like this, which is written as red color. Now apply Routh tabulation formula. Here, if we want to calculate the value of the element of this particular position, then we have to multiply this to this and this to this and then divide with this value. That means 1 into 3 minus 9 into 1 divided by 1. Put the value here. Again, if we want to calculate for this particular position, then 1 into 16 minus 10 into 1 divided by 1. 1 into 16 minus 10 into 1 divided by 1, and that will be 6. Okay, and this way we calculate the s square row, the value of the s square row. So 6 into minus 6 into 9 minus 6 into 1 divided by minus 6. Put the value here. Next, if we calculate for this particular position, then it will be minus 6 into 10 minus 0 into 1 divided by minus 6. So that will be again 10. Put the value 10 here. Like this way, just go through all the process and you will get this type of array. And you will get this type of array, which is very important for stability condition or calculating the stability criteria, which is very important. So if we see or if we want to calculate the stability of this particular section, then we have to see the first column. We have to see the first column. Now if we investigate the first column like this, then we see the elements of the first column are 1, 1, minus 6, 10, 12 and 10. So all the values are positive except minus 6. So there is one sign change. So if there is any sign change, then the system is unstable. That's why the system is unstable in nature. Now, as we all know that if the system is unstable, that means there are some poles which are present in right half of S plane. That's why the system is unstable. Now the question arises, how many poles are present in the right half of S plane here? So just look at the first column and find how many sign changes are there. Here two sign changes are there. Where? Here 1 to minus 6. In second column, in second row it is 1 and in third row it is minus 6. That is positive to negative. One sign change. And in row 3 and 4, minus 6 to 10, there is another sign change. Here sign change is positive to negative and here the sign change is negative to positive. That's why there are two sign changes are present. That's why we can say that there are two sign changes. That's why two poles are present in the right half of S plane. Therefore the system is unstable. Now if we calculate the poles from the characteristics equation mathematically and put the poles in S plane, then we can see these two poles, these complex conjugate poles, are present in the positive real axis. That's why the system is unstable. Okay. Let us take another example. Here one characteristics equation is given, that is s to the power 4 plus 8s cube plus 18s square plus 16s plus 5. Now this is our characteristics equation, and let us check whether the system is stable or not. Just write down the Routh array. Here the highest power of s is s to the power 4, so s to the power 4 will be there, and the row value of s to the power 4 is alternatively we can write as 1, 18 and 5. That means the coefficient of s to the power 4 and coefficient of s square and coefficient of s to the power 0. Now the coefficient of s cube will be 8 and coefficient of s to the power 1 will be 16. Now if we see this type of row, here we can see that this row we can divide by 8. If we divide this type of row by 8, then it will be easier for our calculation. Then we can write this row like this, 1 and 2. That means we have to divide this row by 8 by common factor, that is 8. And now going to our next row, just take the new value of s cube, that is 1 into 18 minus 2 into 1 divided by 1, that will be 16. So 16 and 5 will be there, and like this way just form the Routh array. Now if we investigate the stability, if you want to investigate the stability, then just check the first column, the elements of the first column, and all the elements are of same sign, that is positive. So we can say the system is totally stable as there is no sign changes. And here is example number 3. Just take one example. Here one closed loop transfer function is given where gs is equal to k by s into s plus 1 into s plus 2, and hs is equal to hs, that means the feedback path transfer function, that is hs, and hs is given as 1. So if we want to calculate the characteristics equation for this particular equation or this particular system, then put the value of gs and hs in 1 plus gs hs is equal to 0 equation, and we can find that after calculation s cube plus 3s square plus 2s plus k is equal to 0. So that is our characteristics equation. So this is our characteristics equation. Now taking this characteristics equation, just form the Routh array. Here the highest power of s is s cube. So starting, we have to start with s cube by taking the coefficient. 1 and 2 will be there, and for s square 3 and k will be there, and for s to the power 1 just multiply 3 into 2 minus k into 1 divided by 3, that is 6 minus k by 3, and for calculation of s to the power 0 just multiply 6 minus k into 3, 6 minus k by 3 into k minus 0 into 3 divided by 6 minus k divided by 3. So that will result k. So if we calculate the stability and the region of k for what the system is stable, so we have to check the first column. All the elements of the first column have to be greater than 0. So here 1 and 3 will be there, which is greater than 0. So 6 minus k divided by 3 have to be greater than 0 and k greater than 0. If these two element value is greater than 0, if we put, then we can find the range of k. So for the system to be stable, we must have the following two conditions satisfied simultaneously. That is, k is greater than 0 and 6 minus k divided by 3 greater than 0, from where we can get 6 less than k. That means if the value of k is in between 0 and 6, then the system will be in stable region. So k, the value of k will be in between 0 and 6. The intersection of the two conditions above gives the condition of the stability of the above system. That is, k is range between 0 and 6. Now, what will happen if k is equal to 0 and k is equal to 6? Just go to the next slide. Now, if k is equal to 0, then from the characteristics equation, we can get s cube plus 3s square plus 2s is equal to 0. So that will be our new characteristics equation. Now, if we see or if we calculate the roots from this particular characteristics equation, then we can see that s will be at, that means the poles or the roots will be at 0, -1 and -2. That means at origin there will be a 0, there will be a pole, and -1 and -2 there will be a pole. And if the poles are present at the imaginary axis, then the system is marginally stable. That's why if k is equal to 0, then the system is marginally stable. Now, marginally stable case is basically an unstable case. So if k is equal to 6, then the characteristics equation become s cube plus 3s square plus 2s plus 6 is equal to 0. That is our characteristics equation if k is equal to 6. Now, if we calculate the roots of this particular characteristics equation by putting k is equal to 6, then we can get the roots are at s is equal to -3, s is equal to plus minus j root 2. So here two roots, that is plus j root 2 and minus j root 2, these two roots are present at the imaginary axis. So that's why the system become marginally stable. So that's why, that will happen if k is equal to 0 and k is equal to 6. So for the system to be stable, the value of k should be range or have to be range in between 0 and 6. So that is our condition for stability. Now moving to our next example, one special case, that is, if one element of this Routh array of the first column of the Routh array is 0, one element, then what we have to do, or how we can calculate the stability of the system. Now let us take one example, that is s to the power 4 plus s cube plus 2s square plus 2s plus 5 is equal to 0. That is our characteristics equation. Now if we construct the Routh array for this particular characteristics equation, then we can find that after going to third row, the first column of the third row is become 0. So that is our 0 element of the first column. We can't continue like this as usual. So what we have to do? So substitute epsilon for the 0 element. So here where 0 is came, just put the value epsilon, where epsilon tends to 0 but not 0. The value of epsilon is very close to 0. So here put the value epsilon. Now taking the epsilon tends to 0, just continue and form the Routh array. Now if epsilon tends to 0, then here 2 minus 5 by epsilon we can get. So here minus infinity will be there and 5 will be there. So if we take the first column elements like this, that is 1, 1, epsilon, minus infinity and 5, okay, then we can see there is a sign change. There is one sign change, that is in epsilon to minus infinity. There is one sign change, and minus infinity to 5 there is another sign change. So there are two sign changes. Therefore there are two roots that lies on the right half of the S-plane. That's why the system is unstable. Okay, so that's all for today's class. In our next class we will discuss some more related workout problems. So thank you so much. Thank you for watching.